A Look into Colorblind Glasses by Rihanna Patel and Cora Lapa.
Around 1 in 12 men suffer from color blindness. Color vision deficiency is caused by defects in the sensory cells of the eye. The gene for red-green color blindness is recessive and on the X chromosome. Since men only have one X chromosome, it is more prevalent in male individuals.
Light is perceived by entering the eye and travels to the retina structure, which is covered with rods and cones. When these rods and cones detect wavelengths of light, signals are sent to the brain, and as a result, the wavelengths are interpreted as color. The color of an object we see is the color of the reflected light. Since only cones are involved with color vision, if there is a malfunction to the cone structures, it can cause a loss or partial loss of perceiving different colors.
How does color vision work? As mentioned, the retina at the back of our eyes has cones and rods. Ahmed Salih's study on ophthalmic wearable devices for color blindness management explains how there are 3 cones, red, blue, and green, and these are used to perceive all light and colors of the visible electromagnetic spectrum.
The cones in the retina are also correlated to short, medium, and long wavelengths respectively. The peak spectral wavelength sensitivity of each cone is as follows. Short is 440 nanometers, medium is 540 nanometers, and long is 560 nanometers. The frequency of each wavelength of light can be calculated using the speed of light equation, c equals lambda times mu. Using this formula, the blue, green, and red wave frequencies run at 6.82 e to the 14th hertz, 5.56 e to the 14th hertz, and 5.36 e to the 14th hertz, respectively.
Louise Small and David Fentonby describe in their paper on color vision deficiency in physics teaching that there are 2 common types of color blindness, protanomaly and deuteranomaly. Protanomaly is the anomaly of L cones, also known as red light. People with proton color blindness have their L cones shifted towards shorter wavelengths. Deuteranomaly is the anomaly of M cones, which is normally seen as green light. People with deuteran color blindness have their M cones shifted to longer wavelengths. Individuals with these types of color deficiencies are associated with having red-green color blindness.
Another less common form of color blindness is tritanomaly, which is associated with blue-yellow color blindness. It can be caused due to aging or glaucoma. Tritanomaly involves the reduced sensitivity in S-cone cells, which is also known as short wavelength light. Individuals with tritanomaly have difficulty distinguishing between blue and green, as well as yellow and violet pigments.
When the light at the wavelength where these cones overlap on the color spectrum is perceived, it activates the cones. This makes the colors perceived in these regions indistinguishable depending on how severe the wave shift is and where the shift is located.
When the red wavelength is shifted closer to the green wavelength, individuals find it more difficult to distinguish between red and green.
Since color is associated with the electromagnetic spectrum, we can use the equation E equals E max times cos kx plus or minus Wt plus theta. There are many components of this equation that lie out of our field of depth in this course, but to simplify the 2 key ideas in relation to color blindness, the wave for red code sensitivity moves left, hence the positive angular frequency value, and theta represents a shift in phase closer to the green wavelength.
When the wavelength is shifted closer to the red wavelength, individuals find it harder to pick apart green and red pigments.
The equation used to represent this shift is E equals E max times cos kx minus Wt plus theta. Since the wavelength is moving to the right, a negative sign is used for the angular frequency. Similar to the red wavelength, the phase constant theta represents shift in phase of the wave.
How colorblind glasses were developed. The first colorblind glasses were developed in 1837, and they used colored filters with red and green that blocked out specific wavelengths where there was cone overlap due to the shifting of waves. This allowed for people to easier distinguish between blurred colors. These glasses were made specifically for red-green colorblindness and not blue-yellow colorblindness.
Currently, Chroma glasses are the leading and main manufacturer of colorblind glasses. They describe the use of a filter which removes the overlap of red and green cones and high absorbency at certain wavelengths that overlap. This absorption level depends on the severity of the colorblindness.
How do these glasses work, you may ask? Chroma's lens tech technology filters out wavelengths of light at specific points where the overlap in color sensitivity occurs. The saturated filters lies towards the colors that colorblind people have more trouble perceiving.
Limitations of Enchroma glasses include people with severe deficiency in red-green cones will not find that the glasses work for them. Studies have been done to see the success of the glasses on colorblind individuals, and the success rates are relatively low, as they do not correct colorblindness but rather temporarily decrease the effects experienced from it while the user is wearing the glasses. The glasses help to improve a colorblind individual's ability to distinguish colors, but does not give the user normal colored vision.